So this one is slightly experimental right now, just in the first stage, so to say. Just doing some exploration of this Kaggle data. So I have not really done much beyond posting one Kaggle notebook, and I've started off with this Sartorius cell instance segmentation. So what exactly is this? We can go ahead and probably look on Kaggle itself. And one second. So yeah, this link should work. I give this link on top. Okay, and he's got 3 4 notebooks over here. So this is the person, Slavek Bile. Yeah, so he's in Poland, and he's put some notebooks together, which is this. He's got 3 of them actually, and this is the competition. So firstly, this data, what it requires is to understand what is RLE, how the COCO format works, and all these things are required. Otherwise, you will not reach anywhere with this data. And after that, it is easy. So after that, it is the after that it is basically Detectron or whatever it is that you want to run with, right? So like he's given a starter. So this guy's code is what I'm interested in, because he's the one who gets into more of explanation of the data format and other things. So his first that where is that? Uh, I don't know how to reach his first one, but anyways, so I have that downloaded here. So that first one is what I have here, and so what he does initially is he's just looking into the data set, and he's obviously using PyCoco tools because the annotations are given in Coco format. So the annotations are given in Coco format, and he is using PyCoco tools. And within PyCoco tools, there is something called the mask mask.py. Okay, this is the so this is the this thing PyCoco tools masks.py, and within this they have given an explanation for RLE. So what exactly is RLE, right? Uh, so interface for manipulating masks stored in RLE format. So what kind of masks will be stored in RLE format? What exactly is the RLE format? So for this particular one second, let me so what exactly is the format? There is one CSV file that I have that I need to. Okay, I think we can pick up any one of these. So this annotation is what is basically the RLE format, right? So you have ID, which is image ID, which is okay. Then you have this annotation. Then you have width height of again images. Then you have cell type, that's just a category ID. Then you have plate time, and all of this we can get into later on. This is not really required right now to understand what this is. So again, the sample ID is basically built by concatenating some of these strings and some of this code over here, so that with sample ID itself you can understand what vessel and all that. But this is not really important right now. So what is important is this annotation. To understand this annotation, and these annotations are of different lengths. Like you see over here, row 14. Uh, this is quite a small annotation. Over here again, smaller annotation. They go till almost 59 in length. Yeah. So to understand this, basically, this guy has given he has given this code. Okay. Uh, then he gets into detectron, and detectron is actually what got me to this particular competition and to this particular code. But I haven't reached that stage right now to do anything with detectron, so I'm just still playing around with their code and trying to understand how this thing works. So first, let's go through RLE, and in the PyCoco tools, this mask file. This is the original comments that they have over there. So the RLE is a simple yet efficient format for storing binary masks. So they don't really mention over here that there are two kinds of RLE which is there. One is uncompressed, and the other is compressed. So uncompressed and compressed RLE. I hope I spelled that correct. Seems to be okay. Yeah, whatever. So RLE is a simple yet efficient format for storing binary masks. So when you have a binary mask, what will you actually have? You will have a image which will be uh, split into two colors basically. Most probably will be black and white. So let me show you some of those images, so that in case you've never seen a binary mask, you can understand what exactly that looks like. Mm. So this is a binary mask. You see at this bottom over here, this is a mask of a cell. It is from this very dataset from Sartorius, and similarly, this is another cell. This is another cell, and if you zoom in, there is nothing much. There is just a mask, and I've converted this mask to look like this. The background is slightly gray, and this cell is very dark. So we can change this. I'll show you in the code also how I have done that. So this is simple stuff. This is basically mask. You see these cells floating around in a darker this thing, and then again over here things are changed. The mask is the dominant color is black, the background, and then this is the cell. So just simple. Okay. So for storing binary mask, RLE first divides a vector or vectorized image into a series of piecewise constant regions, and then for each piece simply stores the length of that piece. So when they say piecewise constant regions, what that basically means is if I and there is a wonderful Stack Overflow uh, post, I think, which is the original one by some guy called Wasp something, Waspinator or something. Let me show you. Where did I move that? One second, I put it over here in the code itself, so that yeah. So yeah. So this is 4 years old. So I don't know. There are other sources which have been given, for this code and things like that. But I think this is the original one. Then which people are creating something out of. So Waspinator, I think he's the one who asked the question and then he himself answered it. Uh, so he's given that. He says information is given here. So that is what we are looking at right now. We are looking at that original code only. Okay. And so then again, for example, given this is the mask. Okay, this is the mask. So what is happening here is first two instances are 0, then three instances are 1, then there is one instance of 0, then again that has changed. So that has become something else. So it has become 1. So if you were to get the RLE for this, then you would probably have uh, just as a guess. I'm not sure if I'm doing this right, but then you will get 3. Then you will get 1 1. Okay, 0 3 1 1 is probably what we will get. Uh, but here we got 2 3 1 1. But I remember somewhere they have given that if the first one is 0, you will, okay, now they got 2 zeros together, right? If it was just, if it was like this, then you probably have this as uh, 0 4 1 1 is what I'm guessing. I don't remember exactly, but I think that that is what it is. Okay, so I'll just leave it like this. Then for okay, 0 and 6 1 1. Why? Because the first one is 1. Okay, if the first one is 1 or it's 0, it's here in the code also. uh, Here it is. A value is 1. Okay, if the first one is 1, if the index is 0 and the value is 1, then you append a 0. Okay, so that is okay. So this is what it is. So this will not be 0. So if I changed it, so this one will be 1 and 4, and okay, so it will be 1 4 and double 1 is what I guess. Okay, and if it is again 0, then it will be 2 3 double 1. Fine. Now so this is the RLE format. So manually we can calculate for smaller ones, right? For the small arrays or the small lists or whatever, we can calculate RLE. Um, then he says the odd counts are always the number of zeros. So the 1, is it a number of 0? No, not necessary. I have not understood this. Odd counts are always the number of zeros. How? Because this last odd count 1 we will have to consider, right? This is not a number of zeros. This is a number of 1. This I have not understood. Okay, anyway, so instead of storing the counts directly, additional compression is achieved with a variable bitrate representation based on common scheme called leb 128. So I read this leb 128 on wiki. uh, I did not read much through it, but yeah, there's a wiki page which is dedicated to this, so if somebody wants to read it, you can read it. Then compression is greatest given large piecewise constant regions. So yeah, so piecewise constant regions. So let's say over here you got so many ones, right? So this compression is greatest. He's saying because obviously you got uh, 6 of these ones and you got a 6. Let's say I had 9 of these. So then you just have a 9 over here. So that is what he means by saying that compression is greatest and all that. So fine, okay, that is okay. Uh, then specifically the size of the RLE is proportional to the number of boundaries in M. Uh, okay, for an image. And then assuming fairly simple shapes, the RLE representation is where n is number of pixels in the object. Okay, hence space usage is substantially lower, especially for larger simple objects. Large n, okay, fine. So then they've got encode, decode, merge, IOU, area, two bounding box. Here they've mentioned uncompressed RLE. So I think I again need to go through this because I think uncompressed and compressed they have given some differentiation. No, only here it is. What about compressed? So I'll have to find somewhere or the other some kind of uh, I think I've already got some links which I need to read through. So I will get that and I will again post it. So this is definitely just a very introductory video right now.